Yeah, we've got a special seminar today, but before I introduce our seminar speaker, I'd like to just take a word of prayer. Let's have a word of prayer. Heavenly Father, just thank you that we're almost to spring break here, and I just want to lift up to you all of these students and pray that this will be a refreshing break, Lord, away from classes and just a chance, Lord, to do some other things or maybe get caught up. And I pray that the students will get some rest along the way and come back refreshed and ready for the second half of the semester. And we just thank you for bringing us to this point, Lord. And Lord, in all that we do here, we just want to lift up this work to you and pray that we'll see that your kingdom is being furthered here in and through our lives, Lord, and that we're to serve you and honor you with all the work that we do, God. And just thank you for Elise being willing to give the science seminar here today. We pray your blessing upon her and her work and her upcoming job, and just pray that she'll be able to continue to glorify you in the work that she does, God. So we thank you for this time today. In Jesus' name we pray. Amen. Amen. All righty, I'm Steve Ball, and it's my pleasure to introduce to you a special student, Elise. I met several years ago, and I guess in university physics way back, and she had some very strong interest that came out in space-related stuff. She ended up taking a cosmology seminar with me in honors. She's in the honors program, and so every other spring I would teach a cosmology seminar, and she took that and she just loved it. And so she decided along the way that she would not only get a mechanical engineering major here at Laterno, she wanted an astrophysics minor. Trouble is, we didn't have an astrophysics minor here at Laterno. We had a physics minor, but I said, Elise, maybe you can get this physics minor. She said, no, Dr. Ball, I really want an astrophysics minor because I really want to focus on astronomy-like topics of physics. I said, well, let's see. And we ended up putting together an astrophysics minor, kind of tailored to the kind of things that Elise was interested in, cosmology seminar. She took astronomy with me last fall and took all the physics she could. So anyway, Elise is going to be our very first graduate this May with an astrophysics minor. And so we're proud of Elise. I'm telling you about Elise. Elise got a special, was it internship or REU?
It was an REU.
REU, Research Experience for Undergraduates, last summer at the Space Institute in Tennessee. And I only learned about this sort of after the fact, but she did some very interesting research work there last summer. And now she's got a job waiting for her after she graduates this May. So she'll be working with the Space Institute after she graduates this May. And anything else I need to tell them about you, Elise?
Not really, I guess.
Well, Elise is an honorary member of the Chemistry and Physics Department, so that's why she's wearing her Chemistry and Physics Department t-shirt today. Let's welcome Elise today.
Hello. Hi. My name's Elise. As from Dr. Ball says, I'm going to be talking today a little bit about my summer internship last summer, which is involving fuel cells, more specifically the PEMEC, which stands for proton-electron membrane electrolyzer cell. So I'm going to try to make some of this information coherent to you guys, so I'm going to do my best. Please bear with me. So for basically the summary of what I'm going to be giving for the presentation today, I'm going to give you guys a little bit more information about my summer internship, kind of the stuff that I did, the people who I worked with. Then I'm going to give you some background information that will be relevant later on in the slides. Then I'm going to give you guys a brief overview of the PEMEC cell, and going to go into talking about some electrochemistry testing. Hope you guys have taken chemistry, or some of you in chemistry right now. Then I'm going to go into the TTLGDL manufacturing, and then CL manufacturing, and then I'm going to basically give a conclusion. But yeah. So this last summer, I worked at the University of Tennessee Space Institute, which is actually where I'm going to be going to grad school after I graduate. I worked with the Nano Help group, which specializes in 3D printing, nanotechnology, and low-cost and sustainable power sources for propulsion. So, fuel cells. But my project was involving the PEMEC, the proton-electron membrane electrolyzer cell, and working to increase the efficiency. The Nano Help group's efficiency for the PEMEC is already at 90%, which is extremely high for greenhouse gas energy efficient energy sources. So that's actually pretty cool. Okay, so I'm talking about an electrolyzer cell. So what's the difference between an electrolyzer cell and a fuel cell? They're basically the opposite thing. Well, they're the same thing, but yet the opposite. While fuel cell takes in hydrogen and it releases oxygen into water, the PEMEC electrolyzer cell takes in water and it puts out hydrogen and oxygen. This is one of the only ways in the world to get pure hydrogen, so it's kind of important and a big deal. So if you actually combine the PEMEC or an electrolyzer cell, I might just start saying that because it's easier to say, but if you combine a fuel cell and an electrolyzer cell, it actually works as a cycle, a constant renewable energy cycle. As long as you're using a clean energy source to power the reaction, then, well, it powers the reaction, but then you get more energy out in the long term. I'll show you the equation of that in a few slides. But as you can see here, for electrolysis of water, once you do the reaction, it outputs hydrogen and oxygen, which the hydrogen can then be used for the fuel cell, plus oxygen, which goes back to water, which goes back to the electrolysis of water. So it's basically a never-ending cycle of energy producing. So for the powered electrolysis cell, they can be form-fitted to fit whatever power source or needs that you want. They can be stacked together, as you can see in this photo. There's a whole bunch of electrolyzer cells all stacked up together, right beside each other. And you can create any length or size of them to create any sort of power that you need. And then hydrogen as an energy source produces 0 greenhouse gases, which is a big deal when we're trying to talk and convert from fossil fuels and trying to look for a new type of energy source. Hydrogen is a really good choice to look at and then if you use solar power as an energy source, then it's completely renewable and it's really good for the environment and stuff. Okay, let's talk about a little bit of background information. Up on screen, I have 2 important pictures that you guys are going to need to reference. First, this is the electrolysis of water chemical reaction. For the cathode side, we have the OER reaction, and for the anode, we have the HER reaction. And then the net overall reaction is. And then we have the periodic table. The important metals or elements that I'll be referencing today are iridium, platinum, and ruthenium. Those are the important elements that you guys need to keep in mind today. They are all precious metals, so they're all really expensive and hard to use, or really expensive and hard to find. That's probably a better word. But the electrolysis of water converts water into hydrogen and oxygen with hydrogen energy as a byproduct. The pure hydrogen that is produced is used as an energy source for a variety of applications, such as spacecrafts, powering homes, powering motor vehicles. You can make the motor into anything. When I was working over the summer, we had a demo RC car that was powered from an electrolysis of water, or a PEMEC cell and a fuel cell that was combined in this diagram that I showed before. And it basically created limitless energy, so it was an RC car that never ran out of batteries. For my work that I focused on the the synthesis of the catalytic materials combining. So how to make the energy, or how to make the reaction more efficient with using catalytic materials. And then I also worked on the manufacturing and the applications of TTLGDLs. So TTLGDLs, just for future reference, is thin tunable liquid gas diffusion layer. I'll explain that all in more detail later. But first, oxygen oxygen evolution reaction, OER. So it's the cathode side of the electrolysis of water equation. It is a limiting reaction that generates oxygen through chemical reactions and using the electrolysis of water. It's pretty straightforward. The catalytic materials of oxygen evolution reaction consist of ruthenium, plutonium, and iridium. Ruthenium has a strong corrosion resistance, but it does not have a large efficiency with this reaction. It has good stability, but not that much good for efficiency, which is what we're looking for here. Plutonium works very well in the beginning. It has a very high spike in efficiency, but it kind of tapers out and has a very low lifespan. But then iridium provides the highest catalytic activity throughout the entire reaction. But it has low stability, but not as much as a low stability as the platinum. But for the testing I conducted, I got that mixed up, so I apologize. This OER is the anodic side, not the cathodic side. So OER, HER. Sometimes I get those confused. I apologize. And then HER, which is the cathodic side, is the transfer of hydrogen, or it's the transfer of hydrogen, basically. For the main catalytic materials of the HER, there's PT, which PT offers strong efficiency and it works well with the materials and the structure and the stability of the PEMEC. But carbon also works well, so one of my forms of research was trying to combine carbon and PT as a catalytic material for the HER reaction of the cell. So let's get into an overview of the PEMEC. So we have a solar panel here, which provides energy to the PEMEC, which then converts the water into oxygen and hydrogen, which the hydrogen can then be used for propulsion power systems. And then the oxygen can be used for the space crew for breathing and stuff like that. This can be used in a variety of applications, such as powering the spacecraft, survival, just powering energy sources. Okay, let's get to the nitty-gritty kind of stuff. Okay, so there's 6 components to the PEMEC. So there's the end plates, there's the current distributions, the bipolar plates, the gaskets, the LGDLs, and the PEM. Or in this case, this is the PEM in this case. So the end plates and the current conductors. The end plates can be either conducted out of aluminum or stainless steel because of the corrosion resistance that we're going to have water flowing through. We don't want to get rust and all that other sort of stuff and get dirtying up the reaction. The main purpose of the end plates is to fix the cell and to apply pressure into the cell. There is a 40 psi pressure that is applied to the cell through the end plates. There are 2 current distributors, which are one for the anodic and one for the cathodic side, that conducts electricity that is necessary for the reaction. They are both constructed from Au-coated copper, so gold-coated copper. The copper is for the conductivity because copper usually has a high conductivity, and then gold because of its corrosion resistance. The bipolar flow channels are both made out of graphite. This is because graphite is a stable element and it won't react with the water in the reaction. But they are for voltage reduction and current control. So, and it also serves as the flow channel for the water. So you see all these lines here? This is where the water is going to flow through into the catalyst layer through the LGDL. And then there's 2 pins here, or 2 holes here that are for 1/2-inch pins. That is to stabilize the PEM while it's being assembled. For the TTLGDL, I don't want to show you a picture of these because I just never got a picture of them. But they are plastic constructed from PTFE material to surround the LGDLs, which is the thin tunable liquid gas diffusion layer, for both the cathodic and the anodic sides. The cathode side is about 8 mils, while the anode side is about 12 mils. The difference in each mil is equal to 25 milliliters. or millimeters, just by the way. But the difference in height is because of the difference in the LGDO for the cathode and anode side. Okay, TTO-GDOs. I bet this is the thing that you guys were dying to hear about with how many times I was talking about this earlier. Anyways, I'm not good at jokes. This is the porous, stable flow channel that acts as the transport between the water and the gases of the reaction. The material for this is made out of titanium because it's a non-reactive pure metal that it's a non-reactive pure metal and it won't corrode and get in the way of the reaction. So for the cathode side, either a custom TTI-GDO or a commercial titanium foil was used, and then for the anode, the carbon paper was used. I'll go into more detail of that in just a few slides. For the catalyst layer and the PEM, the catalyst layer is the jump starter of the reaction. It's the one that gets the reaction to initiate. The higher the conductivity, that's the word again I can't say, of the catalyst layer, the greater the efficiency of the reaction there will be. Like the gasket, I don't have a picture for this really. I have a picture of it kind of in a few slides, which I'll point out to you guys for sure, but yeah. But like the gasket, the catalyst layer are different for both the anode and cathode side. Did I get that mixed up again? I was right the first time. I'm like, that must have been a typo on that first slide. Yeah. So the cathode is the oxygen evolution reaction, and the anode is the hydrogen evolution reaction. I am sorry for the slip up and the typo, by the way. But the cathode, we use iridium, as I stated before, and the anode, I use the platinum-carbon mixture. And then a naphthalene-based membrane is the PEM, which is the proton-electron membrane of the PEM-EC. It allows for proton penetration between the cathode and the anode side. So, let's get into the fun stuff. Electrochemistry testing. For the synthesized catalyst layers and the TTO-GDOs, they must go through ex situ and then in situ testing. Little background, ex situ testing means testing outside of the cell, in situ testing means testing inside of the cell. I hope that's okay to follow. But anyways, there were two ways of ex situ testing I performed. There was 3 electrode system, and then there was individual performance testing. The data was collected for these tests using a electrochemistry computer software system. The 3 electrode system, as the name indicates, there are 3 electrodes. 1, 2, 3. The first electrode is the working electrode, which is what we're working with. In this case, it was either the iridium or the PP carbon. The next was the working electrode, which in our case was silver chloride. And then the last one is the counter electrode, which, yeah, and the last one, the counter electrode, was pure platinum foil. And then there was an electrolyte, which is the entire solution. For our testing, we were using an acidic solution for the testing. You can either use a basic or acidic solution for the 3 electrode system, but they each have different results and they have different, trying to think of the word. It has a different caliber, different measuring system for each one. So we were using an acidic system, so we were using sulfuric acid for our electrolyte. And then while the working electrode is submerged, it's not completely submerged, it's only partially submerged in the solution. It can only be submerged for up to 10 hours before the current density starts to degrade, and that can affect testing. But for the catalyst layer testing, the working electrode, the 3 electrode system testing procedure can test both the OER and the HER separately by using the different catalyst materials for each reaction. The procedure is as follows. You'll first start with the OCV testing, which is open circuit voltage testing, and then move into the LCV, which is linear sweep photometry testing, which looks for the current density based off of the current voltage that the cell is producing. And then finally, we'll do CP testing, which I'm not trying to pronounce that. Please don't make me. And which is looking for the stability of the reaction. And here's a graph that I actually made. It was kind of fun. But currently, so when we're doing testings, we're looking for a current density of 10 milliamps to look for the overpotential, which is, current density, yeah, to look for current density, to look for an overpotential of 200. Sometimes you just need to slow down because your thoughts get all jumbled up. But anyways, you need to look for current density in milliamps to find the overpotential in millivolts by milliamps. The overpotential is basically the main thing that we're looking for. Different materials have different standards for placement, like where should this lie in the range. For iridium-based products, it should fall between 290 and 320 millivolts per milliamp. That is really good. For overpotential, the lower the number you get, the better it is, because overpotential is the wasted energy that's in the reaction. So the smaller the overpotential, that means the better the reaction is. Okay, ex situ testing. There we go, both videos are going. For ex situ testing, for testing the CL, the 3-electrode system will work, but for the TTL-GEOs, we can't really do the same procedure because we can't really put a piece of titanium foil in the solution, which is supposed to test for conductivity of this because it's not conductive with the materials. But anyways, I'm going on. I get a little rambly sometimes. But the TTL-GDLs is assembled within the PEM-EC, and then it's tested through that without the CCM, which is the catalyst-coated membrane, which is the combined version of the catalyst layer and the PEM. The water bubbles, so it's assembled in the PEM-EC, and then water is sent through it, through the bipolar flow channels, and then the water bubbles are observed. Basically, we want to see how fast the water bubbles are flowing, the consistency of them, and just how they are looking overall. So, for the LGDLs, it's so important to know that the reactions for the reactions for the cell take place along the edges. So, you can see here that there's a lot of tiny water bubbles along the edge of this triangle, but along the circle, yeah, there's a lot of tiny water bubbles, but there is not as many. And also, this is just a small, like, nano image of the TTL-GDL. If you look at the overall TTL-GDL, you can kind of see it from here, but there's a triangle here, there's a triangle here, and there's a triangle on the other side. There's a lot less edges on the triangular side than on the circular. So the triangular has a higher porosity than the circular one. So the triangular TTL-GDL gets better results because of that.
How big is that triangle or that circle?
It's about 900 nanometers. Oh, I'm sorry, I didn't put a scale up there. But the, for in situ testing, which is testing within the cell. So we have the entire cell is assembled by this point, and we're just flowing water through the bipolar flow channels into the TTL-GDL, through the catalyst layer, through the PM, and we perform these testings. There's a little bit more testing that's involved through the in situ testing than the ex situ testing as expected. So this is the full list of the testing that we go through. We go through OCV and then LCV. Then we're going to go through 2 rounds of CP and MG. CP, I said before, which it conditions the cell and looks at the stability. The MG looks for the performance curve of the cell, which is what you can see right here. This is an MG graph. And then we're going to go through GEIS and then SGEIS, where GEIS looks at the resistance of the whole cell, while SGEIS looks at the fluctuating resistance of the cell. So when it's fluctuating, what is the resistance? Yeah. Anyways, so you can see a bunch of different pore sizes versus porosity. This is of a TTL-GDL test that they are doing as an in situ testing. And TTL-GDL can be in situ or ex situ, but it's most commonly ex situ because of why would you put it in the cell if it doesn't work? These are all like the best ones, and we were just looking for different reactions from the best one. So as you can probably see, the A5 one, which has a large pore size, but about 30% porosity, is the best one that is performing in this graph, but we have other testings. This is an old graph that I was allowed to use. But anyways, for the TTL-GDL manufacturing, there is For the cathode, there's two different ones you can go with. You can go with the TTL-GDL Plus, which is from the picture I showed you guys beforehand with the bubbles and the stuff like that, the fun video thing. And then we have titanium felt, which is, you can see from this top video here. So we ended up going with the titanium felt over with the TTL-GDL because we were limited, we are mechanically limited with cutting shapes that small, and we found out by using the titanium felt, which was just a normal commercial titanium felt for the PEMEC research industry line thing. But anyways, it would actually had better results and performance than the house-made manufactured TTL-GDL. For the cathode side, the anode side, man, I'm getting these mixed up today. I apologize. For the anode side, we used carbon paper, which it was to carbon paper. Carbon is a non-reactive element in this reaction. So this is more to not react while also to power the reaction. But the higher the porosity of the TTL-GDL, the higher the efficiency of the reaction. But you can't have like a giant circle for TTL-GDL and like it's gonna flow through here. No, you can't really do that. You have to have like a stable, like spiral wick grid going throughout. So the highest porosity for the house-made manufactured TTL-GDL that we used was about a porosity of 51%. Sorry, and that showed to have the highest porosity of the testings that we did with that. But the carbon paper had a higher value for efficiency because of that. And then the carbon paper, this is a picture of the carbon paper, by the way, using a electron scanning microscope. So for the carbon layer manufacturing, you have to first prepare an ink, which for that you make an ink for the carbon. To make the catalyst layer, you have to first prepare an ink. This ink is the catalytic ink used to apply to the PEM, and then you test from there. So there are two different ways to prepare the ink. One was the more straight line testing, and then the other was a type of testing that we were researching and we were curious, how would this work? So the first one is a hot press method, and the second one is a spraying method, which I'll go into detail in the next few slides. So to prepare the ink, you have a series of ingredients, 4 ingredients, and the ratios for this depend on the testing procedure that you're doing and the cathode/anode side. So you always have the catalytic material, which is either iridium or platinum, 5% weight of naphthalon, because the PEM is made out of naphthalon, and it would use to bond when using for these applications. IPA, which is isopropyl alcohol, and then distilled water. The hot press method. So after the ink is prepared, you can use the hot press method, which basically you have your PEM sheet, you drop it on and you apply it through that, and then you kind of sandwich it inside the hot press. You can see right here, and by using extreme heat and pressure, it fuses the catalyst layer to the naphthalon sheet, which is PEM, and that's how you can use it for testing. If you guys are curious, the weight and the pressure and the temperature is 135 degrees Celsius and 1 ton of pressure. You can see the pressure on here on this gauge. This is measured in tons, so it's currently up over there in that. But okay, the second method is the spray-on method. So while the hot press method has a little bit more of a solid mixture to it, the spray-on method has a bit more of a liquid mixture, as expected, because we're using a nozzle to spray onto the PEM, as you can see. So this is the PEM originally before it has anything sprayed on it. It's a clear sheet that's made out of naphthalon, and it allows the protons. And then we use the catalyst layer, the catalyst ink, to spray onto the PEM to create the catalyst layer. So this method is faster, and it's easier to be performed than the hot press method, which takes a lot of time, it takes a lot of setup, and it's a little bit more dangerous in some aspects than just a simple spray-on catalyst layer. So, the results of my experimenting. So after the 3 different concentrations, after creating 3 different concentrations of each sample to use for each test, so I had 3 for hot press, 3 for spraying on, we found out that the hot press method still worked better than the spray-on method. Even though the spray-on method was easier to apply and it was quicker, the hot press method still did better, but I didn't get to stay, I had to leave, but they're currently working on a way to improve the spray-on efficiency to have an easier application method with the same results as before. But anyways, thank you for coming. I had a great time in my internship this last summer. I learned a lot. I'm going back there for grad school next year. I'm not working with the same group, sadly. I think the group I'm working with is called Horizon, and I'll be working with advanced nuclear rocket propulsion. So I'm looking forward to that. And then I want to let everyone in this room know that you guys have a chance at getting an internship. They are fun. There's industry-based one, which I had a few industry-based internships, and that was fun. But then I also had a research-based internship, which was also a lot of fun. I got to meet new people. I got to explore around Tennessee, and I had a great time. But that officially concludes my presentation, and I'm open to any questions. Yes.
Can you, I don't know, what is going to be advanced nuclear rocket propulsion? Just, that sounds really fun.
I'm honestly not sure. I started the GRE project for that, so I'm curious on how that's going to entail, but I've not heard anything back from it. It's just that NASA's currently looking into like nuclear rocket propulsion for Mars space travel, and yeah. So I'm looking forward to that. I don't know anything about that yet. That's why I'm going to grad school, though.
How many people worked in your group this last summer?
2.
Just
Me,
2 of you?
I was one of 2.
2 students or just another faculty member?
2 students.
2 students.
We had, so the PhD students that they were not always students, the doctors that I worked with about 4 doctors on this project last summer.
So those were 4 faculty members at the Space Institute, and 2 of you students working.
Yes. Yes.
So when you do this research for the fuel cell and stuff, how does that relate to space?
Well, the fuel cells are hopefully going to be used inside of, we're looking at them as let me go to the picture, this one. So the fuel cells we're looking at as a viable option for a new propulsion system for a rocket engine to be specific. So by using the fuel cells, it can produce oxygen for the crew to breathe, and then the hydrogen goes from the propulsion systems. So by doing a cycle for fuel cells and hydrogen, or fuel cells and electrolyzer cell, then that's basically a limitless source of energy as long as you just keep pumping in some oxygen for the fuel cell. And then that can just produce hydrogen limitlessly, which can be used for the rocket engine. And then most rockets nowadays have solar panels set up on the outside of them, so it would just be a pretty easy switch, but we're still currently looking at the power source for that and doing some testings. Yes.
What's the current lifespan of your cells?
Current lifespan, each cell differs from cell to cell, so I would say about 10, for each catalytic material that you would use, they're about 10 to 20 hours each. So the cells have a very long lifespan, like let me bring up a picture. Did I put where was that picture? So this is the PIM cell. We can use this PIM cell for years and years. The only thing that we're going to have to replace is the catalyst layer, which is the quickly degrading part, but it's also the expensive part of the cell. So we were using iridium and plutonium, which are extremely expensive materials. Like 1 gram of platinum that I was using was about $1,000. So, if that puts things into perspective on how expensive these materials are, we're currently looking at non-precious metals to try to reduce the cost, but the efficiency for these non-precious metals are not very good whatsoever. Hence why we were trying to combine carbon with platinum to see if it has a similar efficiency to just using plain platinum. Yes.
You said earlier that you had an RC car with the setup with the electrolyzer and the other cell. Is that you said it could basically have infinite energy or energy for a long time?
Yes, since there's oxygen in the air and I'm sorry, I keep moving back. Since there's oxygen in the air, the only thing that's required to power it is the solar, which is a solar panel which was set up on top of the car. And by doing that, it basically could run indefinitely.
But it's still getting power through the solar panels.
The solar panel powers the reaction, as you can see in the net overall reaction. It takes some, well, you can't see that reaction, but it takes some energy in the reaction to actually jumpstart the reaction. So it's just enough energy to jumpstart the reaction, but the solar cell does not have enough power to actually power the car.
Okay.
Okay?
All right, let's thank our speaker again. We have a break next week, and then after spring break, we'll have a couple of our own faculty members giving science seminars. We've got Dr. Balmer giving the next one on Thursday, March 19th, and then Dr. Scott Dyer will be giving one the following week. We'll have a special science seminar coming up on April the 2nd. One of our graduates from 1998 from Toronto University is now the chair of the physics department at Clemson University. He's going to be coming to give the science seminar on astrophysics that week. And so we've got a number of interesting science seminars coming up in the second half of the spring semester. So, oh, by the way, we'll be meeting in the Joyce Room. If you want to join Elise for lunch, and we encourage you to come down and go to lunch with Elise. And otherwise, have a great spring break.
I'm just exiting out.
Don't log out of the computer.
I was going to take the bird, and
Okay.
we went to the bounce park. Anyways, I just wanted to say hi.
Oh, hey.